afternoon. My name is Sieber, Arne Sieber. Today I will be talking about oxygen sensors for rebreathers. Okay, so about me, just a few words about me. I am a diver. So this is many years ago. I learned diving from my parents. So we typically went somewhere in the Mediterranean Sea. So all my life I was a diver already. And later it was like this. I used to travel with my van. We had a compressor in the back. We had diving tanks in the back. For me, I never liked diving bases. Sorry if I'm now saying something what somebody doesn't like, but I don't like diving bases. For me, diving is something that I do individually. I like to go to places where nobody else is, and there I like to go diving. I am not a technical diver, even though I did some technical dives, went in some caves. But if I should describe my type of diving, it's recreational. So we are doing it for fun. We want to stay, maybe make a 60 minutes dive, 90 minutes dive, but all in some kind of recreational limits. So yeah, Italian recreational limits, so maybe 50, 60 meters depth or something like this. Yeah, in Italy it is like this. So there it starts to be interesting. So open water diver goes to 50 meters. So that's how it is. So anyway, this was the situation, and you know, I had this small Bauer compressor, quite an old one, 2-stroke motor. You know, every time it took quite a long time. The whole thing was running, and charging the tanks was really a pain in the ass. So I got annoyed with that, and especially later on. Then you know, we like to spend weekends outside with a small Zodiac in a tent. So we had tanks with us, but you know, the amount of diving was quite limited with that, because how to refill the tanks? There was no diving base, nothing else, and I couldn't put my compressor on that boat. So that was the moment where we said, yeah, we need to have an alternative. So it doesn't work with the rebreathers with the tanks that we have, but rebreathers, that would be a nice solution. As it was just introduced, I'm not only a diver, but I'm a biomedical engineer. And at that time, I was working at the Institute of Clinical Physiology in Pisa, and we were working all the time on divers, so making all kinds of measurements, starting from ECG on apnea divers, or measuring the oxygen saturation in the blood of apnea divers, or making blood pressure measurements. So this was my daily stuff. And at that time, I started more focusing on rebreathers. So what I want to talk today about is a bit about sensors in rebreathers. So I would like to give you a little bit more understanding of oxygen sensors in the rebreathers, what type of failure modes there are. I will talk a little bit about validation versus voting. I want to talk a little bit about electronics in rebreathers, and then I will give you a short glimpse about future technology, future sensor technology that might come in the next years. It's still on an academic level, but it's, in my opinion, it's a question of time till new things will come up. So, rebreathers. So, rebreathers for me, rebreathers was, I want to have long autonomy, so meaning I can do 2-3 dives without charging the tanks. Rebreathers are great for making photos. It's silent. It's a typical, it's a totally different way of diving. It's an increase of the quality of a dive. You have warm breathing gas. I wanted to have a small and lightweight system. This was something very important for me. And then there are the mechanical and electronical ones, different type of rebreathers. But one main problem that I saw as a biomedical engineer is gas sensing. So at that moment, I was trying all types of rebreathers, small rebreathers. I was looking for a recreational unit. So I was trying the Draeger units, for example, but I wasn't really satisfied. So we started into developing our own recreational rebreather, and this was then the one version we came up, and with which one we enjoyed very much diving. So you see Milena, my lovely wife, and she is preparing there just one of the rebreathers. It's a very small unit. It's still an experimental unit, but this was our recreational rebreather that we used for our dives. And it was actually the first rebreather that we know about which had this true sensor signal validation. And I will tell you now a little bit how it came to that and why we believed that this is the way to go. So, a picture, I don't think that we have to talk about this very much. So, in a rebreather we have a breathing loop, and the oxygen sensors have a very, very essential role in the whole thing, because they measure the partial pressure of oxygen, and all the control is based on that. So, but I said that I'm a biomedical engineer, and my background is sensor technology. Before coming into the diving market, I was working for the medical field in the field of diagnostics. So sensor development for diagnostics. And now in the last days, we had many times, we brought the car industry into the game. When we said, when we were comparing rebreathers with the car, we want to have electronics, like in a rebreather, it should be fine. We want to have a car, it should work like a car. But I like to compare it a little bit with something different, with the medical industry, because this is also something quite similar. The medical industry, here we see a product I was working on. It is an analyzer from the company called Roche Diagnostics. This system is measuring all kinds of blood parameters. Also oxygen, carbon dioxide in the blood, just an example. But what I want to say is, here inside we have sensors. We are measuring parameters on the sensors. And now, depending on what we measure, the clinician or a doctor, they will do some kind of a certain treatment. So what that machine brings may be quite substantial and have some kind of substantial effect on the patient if the machine is measuring something wrong. So there are some kind of similarities with a rebreather. If the sensors are not working correctly, this can have a very bad outcome for the patient, or in a rebreather for the diver. So there are some points what we as developers of such systems always had in mind. The first thing was, do not abuse the sensor. Do not use the sensor in environments what it is not made for. Then calibrate the sensor under similar conditions as during measurement. What I want to say is, with that is, if I want to measure, for example, 5 milliliters of glucose in the blood, I do not calibrate at 25 milliliters. I calibrate at 5 milliliters. So to be somewhere there where I really want to measure. So calibrate in the measurement range. The next point is, do a multiple point calibration. So define a span, and within this span I want to measure. I make a calibration point at the bottom, I make a calibration point at the top. This is the minimum what I want to have, to see if I'm somewhere in the correct range. And then another very important thing, have the same temperature during the same sensor temperature during the calibration as during measurement. So, and one very important point, and this is not written here, but it's very important. If you look at these systems, yes, they calibrate automatically. They calibrate maybe each 2 hours, each 4 hours. But what they do, before and after each measurement, they make a sensor validation. So they flush the sensor with a liquid with a certain amount of gases, with a certain amount of ions, and by doing this, they can see if the sensor is working correctly. The next thing is that this system is not, we don't need a nurse who comes with a checklist. The system is doing all the tests automatically. At the start of the system, it goes through all the tests and tells you if it's ready to measure or not. So at that point, I was thinking, why not to take all this technology and bring it into the rebreather? So, but if you compare this now to the oxygen sensors that we use in diving, well, first of all, we use the oxygen sensors in harsh conditions. We abuse the sensors. And with that, I mean, well, we expose them to shocks. With shocks, I mean, we put the rebreather on the rib is jumping from wave to wave, and this is not good for the sensors. We expose them to high temperatures, to high pressure. And you have to remember, this is all outside of the manufacturer specification of the sensor. The next thing is, we calibrate the sensor at 0.2 or maybe 1 bar PO2. And we're doing this at ambient pressure. So, but then when we are diving, we use the sensor up to 1.6 bar and the temperature's up to 50 degrees. I mean, if it's at the exit of the scrubber. So, you know, this is not the same like what I have learned in the medical industry, how you should treat sensors. And this is then when I said, this is not how it should be. So, here comes my first message for today, my first take-home message. Rebreathers use sensors outside manufacturers' specifications, and guys, don't blame the sensor manufacturers if the sensor fails. I mean, it's outside specifications. And if you look then, the rebreather market is so small in comparison to the medical market, and this burden of liability is actually then what forces then the sensor manufacturers not to sell anymore to the rebreather industry anymore. If the divers come up and say, hey guys, my sensors don't work, so you are liable for that? Well, they are not, because you use them outside of the specifications. So, understanding PO2 sensors. The sensors that we are currently using in a rebreather are galvanic oxygen sensors. They are standard in diving, and important thing is the anode material. The anode is typical lead, is oxidized in the sensor, and the sensor is working like a battery, like these typical hearing aid batteries. It has limited lifetime. So if you look now into textbooks for rebreather diving, you typically find such chemical equations which describe how the sensor should work. So we have oxygen going through the sensor membrane, and what happens? This oxygen is oxidizing the anode. The anode is a lead block inside the sensor. So here you have a sensor cell which is open from the back. The board for temperature compensation is removed so that you can see inside. And what you see here, this brownish stuff, this is actually the anode, the lead anode. And this anode is oxidized over time. So for each molecule of oxygen, we will end up with 2 oxidized molecules of lead. And what we actually measure in the end are these 4 electrons. And these 4 electrons is a sensor current, and we drive this current over a resistor, and this is what gives us in the end a millivolt reading. If you look now at this sensor, you see there is the lead and below, and there is, I don't know if you can see it well, but there is some reflecting light, and there is a membrane above that lead. Below, there is electrolyte and this lead anode, but there is a membrane above that, and that membrane is there to allow a pressure equalization. So this is very important in order not to get false readings. So here comes take-home message number 2, and this is now especially addressing rebreather manufacturers and home builders. So avoid any differential pressure between the sensor membrane and the backside, because if you have there a differential pressure, you will see that in the signals. So the one equation that I showed you before about oxygen sensors that show in principle the functionality of oxygen sensors, so that oxygen is reduced and we have 4 electrons. This is an electrochemical reaction that is absolutely not linear. But we all know that a signal that we get is rather linear. So the question is, how do we get that? And electrochemical engineer, he applies there a trick. And what he is doing, if we look at the sensor, so this is the sensor housing around, and there we have this anode material that gets oxidized. In front of this, we have the electrolyte, and what then happens is we have here the cathode. And at this cathode, the oxygen goes into the electrolyte and then is oxidized in the anode. So this is non-linear, but the electrochemical engineer applies now. Someone have the laser pointer. What we have here is the cathode, and the cathode is like a mesh, but now we put in front of that the sensor membrane. And the whole thing now here in front acts like a diffusion membrane, like a diffusion barrier. So what happens now? Oxygen is diffusing through this barrier and gets dissociated and reduced at the cathode. The cathode is here, this mesh here. All oxygen molecules at this cathode get dissociated, so the PO2 at this point, at this cathode, inside the sensor here, is close to 0. So what we achieve now with doing this is that the sensor current becomes proportional to the diffusion of oxygen molecules through the diffusion layer. So this is now a mechanism that is only dependent anymore of a diffusion law. So it's not an electrochemical process anymore. What we have is that the diffusion of oxygen molecules is now linear to the PO2 in front of the membrane. And there is a linear relation between the PO2 and the sensor current. So with this type of sensor current, sensor assembly, we get a linearization of the output signal. And what we have is we have a sensor current that is only dependent anymore on the diffusion law. The diffusion law, the fixed law of diffusion. So temperature and oxygen sensors, in a rebreather, the PO2 sensors are exposed to temperatures from possibly 0 to 50 degrees Celsius. So 0, for example, if I'm on a nice mountain lake and it is in winter and I take the rebreather out of the car and it's cold, it might have 0 degrees, and then I start doing the calibration. I start with 0 degrees centigrade, and then at the exit of discovery it might have 50 degrees. So the diffusion through the membrane, the diffusion of oxygen molecules through the membrane is temperature dependent. And this is typically something like 2 to 3% per degree centigrade. So the sensor current is in theory proportional to through the diffusion of oxygen molecules through this sensor layer, which means that in the end the oxygen diffusion and also the sensor current rises with 2 to 3% per degree centigrade. So I have here a nice picture from Paul's excellent article about oxygen sensors. I think you can download it from his webpage. This shows how the sensor deals then with these temperature changes. So the sensor is a current source, so we measure electrons. And here we have a network of resistors and a temperature sensitive element, this NTC. And with this kind of network, we can achieve a temperature compensation. So ideally, this type of sensor will always produce the same millivolt signal, independent on what type, under which temperature it is. So today, Bill Stone showed the picture of these two sensors that were deviating from each other because of different temperatures. One important thing is if you look at these sensors and these resistors, they all have certain tolerances. So even if they are assembled correctly, it might be that you don't achieve a perfect temperature compensation, especially if you calibrate the sensors at a completely different temperature as you use them in the end. So there we come then to the sensing problem. So important for the sensor is, does the galvanic sensor have the same temperature as the sensing element? So typically in such sensors, the sensing element is mounted on a small PCB on the back of the sensor. So in a sensor for a rebreather, you put in some kind of thermal conductive paste in between this PCB and this membrane at the back, so that you have a very good thermal conductance between the temperature sensing element and the electrochemical sensor. So this is for a sensor that you use in a rebreather. But there are a lot of sensors out in the medical market that are not made for usage in a rebreather. What was it? Okay. Interesting. So is this a sign for me? I don't know. Okay, so there are sensors in the medical market that also have this temperature compensation circuit, but they do not have this paste in between because you don't need it. You have them all the day in a clinical setup, all the time at room temperature, so that you don't need it. But if you use this now in a rebreather, actually then you have a big problem, because there you suddenly have temperature changes during the dive, and you cannot guarantee that the board has the same temperature as the cell. So there comes my next message. Do not use medical oxygen sensors or oxygen sensors that are made only for nitrox analyzers in rebreather diving, because you don't know, without assembling them, if there is this conductive paste in there. The next thing is rebreather design. Avoid temperature gradients inside the sensor. So if you have one part of the sensor that is cold, the other side that is warm, you have some kind of gradient, and you don't know if the sensing element of the back has the same temperature as the sensor cell. So you will get some wrong readings. So the next thing is response time of sensors. Typically when you read data sheets of sensors, you read values like 6 to 10 seconds response time of a sensor. But this is at ambient, at room temperature, 20 degrees for example. As I said before, the mechanism of the sensor is based on diffusion through oxygen diffusion through this layer. And this takes time. And this is very strongly temperature dependent. So if you make the calculations, you will see something like that at room temperature, the sensor might have a response time of 6 seconds. If it's even warmer, it will go down maybe to 3 seconds. But what happens if you go close to 0 degrees? The response time will rise. And it can go up to 25 seconds, for example. So keep this in mind when you want to do a calibration or something like this. If the galvanic sensors are very cold, their response time is very slow. So next important point is anode exhaustion, or generally the failures of sensors. Anode exhaustion, A current limitation is the one what we speak about most of the time. Next thing is cathode poisoning. The cathode gets passivated, you get wrong signals. Mechanical problems, leaking of the electrolyte, damage of the sensor. For example, if you have a small hole in the sensor membrane, more oxygen can go in, so you have higher currents. Or electrical problems like corrosion or component failure. Electrical interferences, these are things what you have to think about. Current limitation. Here I have again a nice picture from Paul's work. As I said before, the anode is the fuel of the galvanic sensor. And once this fuel is exhausted, the sensor will not work anymore. So current limitation now describes this effect when not all oxygen molecules that reach the cathode are really reduced. So what happens is, if you look now at this blue sensor, this is still a sensor that is quite good. So we increase the pressure, the partial pressure of oxygen in front of the sensor membrane. And here we read the current. And with increasing the partial pressure, the current is rising. And it's rising and it's rising till to a certain point when not all the molecules can be reduced anymore, and then the sensor gets limited. It cannot produce a higher current. And now if the anode gets older, gets exhausted more and more, this level is sinking. So at a certain moment, this is then a really badly current limited sensor above, maybe here, 1.3 bar, something like this. It cannot read any higher signals anymore. So how do you do that now? How do you test them? One thing is checking them in these cell checkers that you all know, and you're checking them at pressures above 1 bar. But now we have one problem, and we have to think a little bit about the interpretation of the results. And here again comes the temperature into the game. So if we test now the sensors and we get a result that this type of sensor, this special sensor, is not current limited at 1.6 bar, then it doesn't mean that this sensor is not current limited during the diving because of temperature. Because you're making this test at ambient pressure, maybe 20 degrees centigrade. But then during the dive you increase the pressure, the temperature of the sensor is increased to maybe 45 degrees. You have a higher diffusion of oxygen through this membrane, but the current limitation is an effect that is caused by the anode. So what can happen is that you have a higher amount of oxygen, but even if you have 1.6 bar, if you can read 1.6 bar on the surface, at higher temperatures, it suddenly doesn't work anymore. It reads lower. So our acceptance threshold is if we say, if our sensors can't read 2.5 bar at room temperature in the cell checker, then we don't use them for rebreathers, rebreather diving. In my opinion, the better approach is testing the cells at 6 meters with oxygen. So take-home message again is do not use sensors in rebreathers that cannot read at least 2.5 bar oxygen, or alternatively test the sensors during the dive by flushing the sensor with oxygen. So, lifetime of oxygen sensors. This is a very important topic. How to specify the lifetime of a sensor. So many years ago, it's not there on the web page anymore, but sensor manufacturers like to specify the sensors in months. So you could read something like lifetime in months at storage, in air, at room temperature, something like between 24 and 60 months. A different way of describing the lifetime is describing it in volume percent oxygen hours. And values that are given is something like 500,000 to 1 million. This is values from cell manufacturers. So what does that mean? What does this unit mean? So you multiply the oxygen fraction in which the sensor is stored with the amount of time. So as an example, storage of a sensor in air for 1 year, 21%, multiplied by 365 days, multiplied by 24 hours, gives us this amount of volume percent oxygen hours. If we use this sensor now in a higher temperature, well, we have learned before that for each degree centigrade we have an increase of about 3%. So we can see 25% multiplied by 365 days, by 24 hours. But now we have this small part here. And then we come to a slightly higher value here at the end, if we store it at 30 degrees. And this is quite a nice explanation why you can say, yeah, if you store it at warmer places, or if you're, for example, in Egypt storing there the sensor the whole day at 30 degrees, it will last shorter than if you have it in Austria at 15 degrees. So, now let's go to diving. And one dive, PO2 1.3 as an example, 20 degrees centigrade. 130, I write here now 130%, so that it fits to this unit. Multiplied by 1 hour, we have 130 volume percent oxygen hours. The same thing at 45 degrees, because inside the rebreather sensor will be warmer, we get a higher value. So, let's make an example. 2 years, 100 diving hours per each year, rest storage at room temperature. So we get this value from diving, this value from storage. But in reality, now if you compare this now to the values that I gave you at the beginning, 500,000, that the lifetime is something like 500,000 to 1 million volume percent oxygen hours, and then you compare it to this value after 2 years. And we all know that the sensors typically last between 12 and 18 months. Then we see that this is far lower than what is specified by industry. So one has to think about this. This is just much lower than the sensor is normally specified. And this actually demonstrates that in rebreathers, you have an accelerated aging of oxygen sensors. The sensors are designed for applications in standard atmospheric pressure, in room temperature, no carbon dioxide. In diving, you have high PO2s, high temperatures, high pressures, humidity, eventually an increased carbon dioxide level, mechanical shocks, corrosion, all kind of stuff that the sensors do not like. Again, a picture from Paul, and he showed here a lifetime of sensors, 1,000 sensors from any batch, and here you can see, yeah, you have a failure at the moment here. You have months of the sensors, number of the sensors, and you see 16, 18, 20 months. This is the average lifetime of the sensor. It's nice, that's how it is in rebreather diving, but this is below what the manufacturers specify. So, why do I tell you this? Let's think a little bit about this voting algorithm. What is done there? We advocate using 3 or more sensors in a rebreather. We compare the sensor signals, and well, there are statistics that show that the risk of multiple sensor failure is relatively low. But all this is based on the assumption that sensors fail independently. So, do we have an independent failure in a rebreather? Who does think that we have an independent sensor failure in a rebreather? Anyone here? Okay, all think that. Okay. In general, this is true, but only under laboratory conditions, when sensors are used within the specifications. In a rebreather, this is different. In a rebreather, the sensor aging and sensor failures are caused by abuse of the sensors. The sensors in a rebreather have a common history. You have the sensors inside the rebreather, and each, okay, maybe you change them in different intervals, that they have slightly different history. But in general, they have a common history. They are all exposed to the same partial pressure, all to the same absolute pressure. So you have a common history. So just assuming that the sensors fail independently and then there is no correlation between the sensors is just wrong. So what can you do now? What should somebody do now during the dive? You should come, okay, you have a manual or automatic vaulting algorithm, minimum 3 sensors. Okay, this is all fine. But what you should do now, you should make all oxygen or diluent flushes just to see if the sensors are really working correctly. You can have 2 sensors showing the same value, but it might be wrong. And the third one, for example, giving the right signal, would be voted out. So you don't want to have that. But by doing, in regular intervals, diluent or oxygen flushes, well, you can validate the sensors, see if this is working correctly. One problem is that diluent and oxygen flushes is something what requires user training, requires some know-how, and it's probably not suitable for recreational divers on a daily basis. So what comes here, and I said I'm a recreational diver, I don't want to do this task all the time. So what here comes into the game is this automatic through validation of oxygen sensors. The one system that I showed you at the beginning, where my wife had this small little unit, inside there was something like this. So you had the oxygen sensor, you had a microcontroller, you had oxygen and diluent, but what we added were two solenoids that could inject these gases directly in front of the sensor membrane. Here you have some data. So this is the depth profile. During the depth, I think it was 120 seconds, we injected either oxygen or diluent onto the sensor membrane, depending on which depth you are. You can see this in these small spikes. Each of these small spikes going down is an injection of diluent. In that case it was air, onto the sensor membrane. And what should happen is that the signal during this injection shortly goes down to this value, and if you calculate the fraction, it should be 21%, and then afterwards it goes up. So by doing this, you can validate the sensors during the whole dive. You get some kind of feedback if the sensor is working correctly. The system knows if the sensor is working correctly. This is exactly what is done in the medical industry in these clinical analyzers. You check the sensors all the time. That's, in my opinion, the only way to really be sure that the sensors are working. Today, you can find this technology in the MK6 rebreather. Here you have two sensors, and if you look now in detail, you can see the sensor membrane and you see a little hole. And this is a part where then oxygen or diluent is injected on the sensor membrane. And I think this is a feature that makes the MK6 different from all other rebreathers that are on the market. Let's leave that behind and let's talk about something else. There is this so-called RoHS directive, and I think it's worth that I talk 2 minutes about that. This RoHS directive is about a restriction of hazardous substances, and it's linked to the waste of electrical and electronic devices. This directive restricts the use of lead, and as I just explained to you before, lead is the material that we use in the sensor for the anode. So there was a recast of the RoHS directive in 2010, and this says now that medical consumables are now also included in this directive, and that it has to apply to oxygen sensor cells. So, what does that mean? Basically, it means that there might come a time when we don't have oxygen sensors anymore, because the medical industry is not allowed to use the sensors anymore. So there might be a major shortage in oxygen sensors starting from 2013, when this recast will be in force. So, there are alternative lead-free oxygen sensors. We are currently testing them. They work quite well, but we have seen that there is some hysteresis in the sensor signal. So the sensors work well in the medical field if you stay at 1 ambient pressure, but as soon as you change the ambient pressure, you get a hysteresis, so it needs some more development. But so if you want to use this in a rebreather, you need further development. But the problem is that the medical industry is big in comparison to the rebreather market, and if this recast directive gets into force, and these type of sensors will be banned, where there are no oxygen sensors for us. So, electronics in rebreathers. This is my next point, what I said. Design of electronics in rebreathers. A very important thing is that the electronics is well designed. Important is that a failure is immediately recognizable. As an example, if you have a head-up display with a red light, as a very simple example, okay, and you have learned that the red light flashes if there is something wrong with the rebreather. So you go diving, you look at the head-up display, but you don't see anything. Maybe the battery has gone dead. The system doesn't work anymore, but there's also no power anymore for the LED. So the system is down, but the LED will never shine because it has no battery anymore. So this is just an example that shows you, hey, take care a little bit about during system design that we don't reach a state where we would need a red light, but it just doesn't work anymore. So what are the approaches? We should have some kind of redundant electronics, or we have networks inside the rebreather where the network nodes, 5 minutes, okay, perform some plausibility checks. And so that we can trigger then warnings. But this only works if the sensor nodes are independent from each other. I go a little bit now this quicker because I was told I only have 5 minutes left. Okay. Just to show you a little bit now, the last thing about future sensors and possible future oxygen sensors. Here we have a nice small little fellow. What happened to this one? The board was removed. We have now a small microcontroller on the back. And what it can do, it can measure oxygen hours. It has the complete history of the sensor stored on that chip. It has a sensor ID, and it can electronically check for current limitations. So we don't need any additional solenoids. We can check it electronically. Optical sensors. This is also a different type of sensor technology that might come. It works like this, that you have some kind of a layer, and you illuminate this layer with a light, and you get a fluorescence. So now, dependent on how many oxygen you have in the gas in front of that layer, you have less fluorescence. So the higher the oxygen level, the less fluorescence you have. Sensors like this are available already for a long time, but they were used for measuring traces of oxygen. So till long time, you could not measure in a acceptable precision above 0.5 or maybe 1 bar PO2. But now there came a breakthrough at the Technical University in Graz from Professor Clement, who has developed such a sensing material which is less sensitive, and suddenly you can measure PO2s above 1 bar with sufficient accuracy. Response time in the air might be 1 to 3 seconds, so quite fast. Might be a good solution, especially when you can do it maybe in a way that you take the sensor and mount it on a scrubber cartridge. So it's suddenly a single-use sensor. Each time that you go diving and each time you exchange the scrubber, you have a new sensor. All these questions of sensor aging suddenly are gone. So this is something what might come. Solid sensor state technology is something different. We have been looking into that for the last years. Oxygen sensors and solid state sensor technology are similar, like the lambda sensor in your car. It's basically working on ceramics that become ion conductive under higher temperatures. So there are sensors that are very small, microsensors, microfabricated sensors, with very small sensing elements, 2.5 by 2.5 millimeters. So they are perfectly suitable for integration into a mouthpiece. There are amperometric sensors for oxygen, but there are also similar size sensors for measuring carbon dioxide. What we have done then is we have built up a prototype. This is a Mark 6 mouthpiece, where between the mushroom valves we have integrated a chamber with such sensors. So this is a prototype that we have been diving. We made calibration of the sensors. So with some sensors we could achieve quite acceptable results. Here you see signals. Here we have the time. Now somebody is breathing just air through the loop. You see each breath, each exhalation, the oxygen level is sinking, and then inhalation again is rising. At the same time, the carbon dioxide level, each exhalation is rising, and then during inhalation, it's falling again. The sensors have a response time of something like 90 to 100 milliseconds. So this is also a very, very exciting sensor technology, but it's still on an academic level, and it will take some time till it might come to a point where it can be used in a rebreather. Last slide, just some acknowledgments. So part of the work was funded by European projects. One project was the Life Loop project. The other one is the FIPOD project, which is focusing on medical technology, medical measurements underwater. We're partially funded by the Center of Applied Technology in Leoben, Austria, by the Austrian Economic Service. I would also thank my co-workers at IMEGO and my research group in Austria. Thank you very much. If there are any questions, if we have time, I don't know. We do.
I would have thought this would stimulate a lot of discussion, because I sense that our O2 sensor technology is being threatened when companies like Teledyne say you can't use it above 1.0 atmosphere? Are we at risk of running out of sensors?
My opinion?
Yes.
Well, I mean, we have seen the story with Teledyne, no? I mean, I think there is a risk of running out of sensors, and I think there's a need for developing a dedicated sensor for the rebreather market. The problem is that the rebreather market is quite small in comparison to the medical industry, and developing a sensor, a new sensor, costs a lot of money. You can't do that just in the field if your only market is the rebreather market. So maybe it changes now with the recreational market if the sales increase, and maybe there will be funds for developing a dedicated sensor for diving.
Okay, I guess that's time for break.